Mars is cold. This is not a casual observation. At the equator, on the warmest summer day, the surface temperature may briefly reach a few degrees above 0°C. At night, it plunges to -70 or 80 degrees. At the poles, temperatures reach -125. The average surface temperature, integrated across the entire planet and all seasons, is approximately -60 degrees Celsius. Mars is also thin. The atmospheric pressure at the surface is less than 1% of Earth's at sea level, equivalent to being at an altitude of about 35 kilometers above Earth, well above the stratosphere, in space that no human being can breathe unaided and in which exposed liquid water immediately boils and evaporates. Mars is also unshielded. Earth's magnetic field deflects the solar wind, the stream of charged particles continuously emitted by the sun, away from the upper atmosphere, protecting atmospheric gases from being stripped away over geological time. Mars lost its global magnetic field approximately 4 billion years ago, when its core solidified and its internal dynamo shut down. Since then, the solar wind has been directly striking the Martian upper atmosphere and has, over geological timescales, stripped away what was once a much thicker, warmer, wetter atmosphere. Terraforming Mars, transforming it into a planet with a breathable atmosphere, liquid surface water, and temperatures compatible with unshielded human survival, means reversing or compensating for all of this. The task is staggering in its scope and has a timescale measured in centuries or millennia. The physics, however, is understood, and serious scientists have produced detailed, quantitative blueprints for how it might actually be done. The first and most fundamental challenge is the atmosphere pressure. You cannot breathe on Mars not primarily because the atmosphere lacks oxygen, though it does, being 95% carbon dioxide, but because there is not enough of it. The total pressure is insufficient for gas exchange in human lungs. Raising the pressure requires adding atmospheric mass. The most accessible source of additional atmospheric material on Mars is frozen carbon dioxide, dry ice, in the Martian polar caps, and carbon dioxide dissolved or trapped in the Martian soil, called regolith. Scientific estimates suggest that if all accessible carbon dioxide reservoirs on Mars were released into the atmosphere, the pressure could potentially reach something between 5 and 20% of Earth's sea level, still insufficient for unassisted breathing, but significant enough to allow liquid water to exist stably on the surface. The mechanism for releasing this carbon dioxide is warming the planet. Mars is in a stable, cold equilibrium. The carbon dioxide is frozen because it is cold, and it is cold partly because the thin atmosphere is an inefficient greenhouse that allows most solar radiation to escape as heat. If the temperature could be raised, the polar caps would sublimate, releasing carbon dioxide that would thicken the atmosphere, increasing the greenhouse effect, which would raise the temperature further, releasing more carbon dioxide, a cascading feedback that could self-sustain once initiated. The challenge is getting this cascade started against the equilibrium. The warming mechanisms that scientists have proposed range from the ambitious to the genuinely extraordinary. The most modest proposals involve releasing powerful greenhouse gases into the Martian atmosphere. Chlorofluorocarbons, the same compounds that damaged Earth's ozone layer before they were restricted, are extraordinarily effective greenhouse gases, thousands of times more potent per molecule than carbon dioxide at trapping heat. Perfluorocarbons and sulfur hexafluoride have been proposed as alternatives with similar properties and less direct ozone-damaging chemistry. Manufacturing these gases on Mars and releasing them into the atmosphere in sufficient quantities to raise global temperature by enough to initiate the carbon dioxide cascade would require industrial-scale chemical manufacturing on the Martian surface. The quantities required, millions of metric tons annually, sustained over years to decades, imply manufacturing infrastructure that does not yet exist anywhere on Mars, and that would require sustained human presence and massive supply chain support. More dramatic proposals involve orbital mirrors. Large, lightweight reflective structures placed in orbit around Mars could focus additional sunlight on the polar regions, directly sublimating carbon dioxide ice and delivering targeted heating. The reflectors would need to be enormous by any current engineering standard, hundreds of kilometers in diameter, but they could be made from very thin film materials and manufactured from asteroid resources without being lifted from Earth gravity well. The most radical proposal, explored by NASA scientists including Robert Zubrin and Christopher McKay, involves redirecting asteroids, large ice-rich asteroids from the outer solar system, impacting the Martian surface, would simultaneously deliver water, volatiles, and enormous quantities of kinetic energy in the form of heat. Each such impact would warm the planet by a measurable degree. Dozens of such impacts, carefully directed, could potentially raise global temperatures by tens of degrees over centuries. The engineering and political challenges of deliberately directing large asteroid impacts are, to put it mildly, significant. The magnetic field problem is the most fundamental long-term constraint on terraforming Mars, because without a magnetic field, any atmosphere created on Mars would gradually be eroded by the solar wind over geological timescales, not immediately, but over millions of years. This problem has produced perhaps the most remarkable proposal in the entire terraforming literature, creating an artificial magnetic shield for Mars by placing a large electromagnetic dipole at the Mars L1 Lagrange point, the gravitational balance point between Mars and the Sun, approximately 1 million kilometers sunward of Mars. A large enough dipole at this position would project a magnetotail behind it that could, under some modeling conditions, encompass Mars in a region of reduced solar wind exposure. The planet would not have its own magnetic field, but would be partially sheltered by an external artificial one. NASA scientists Jim Green and colleagues published a paper on this concept in 2017, acknowledging that it was speculative but arguing that the physics was not prohibitive and that a solar-powered electromagnetic structure at the L1 point was not beyond the engineering range of a civilization significantly more capable than our current one. Their modeling suggested that with such shielding in place, the Mars atmosphere could thicken to about half Earth's current pressure over centuries as carbon dioxide was released and the solar wind stripping rate was reduced. The biological phase of terraforming, introducing life to a Mars that has been warmed and had its pressure increased, but still lacks oxygen and has high carbon dioxide concentrations, is in some ways the most tractable part of the problem. Extremophile microorganisms on Earth survive in conditions far more hostile than a warmed, pressurized Mars. Cyanobacteria, which were responsible for producing Earth's oxygen atmosphere over approximately 2 billion years through photosynthesis, can survive significant radiation exposure, extreme temperature swings, and chemical conditions very different from the moderate environments most life prefers. Releasing engineered or selected cyanobacteria into a partially terraformed Martian atmosphere would, over timescales of thousands to hundreds of thousands of years, gradually convert carbon dioxide to oxygen. The process is slow by human standards. By planetary standards, it is relatively rapid. Earth's own oxygenation required about 2 billion years with unengineered organisms. On a planet already hospitable to life, Mars, with directed biological intervention and engineered organisms, might achieve breathable conditions in far less time. The full terraforming of Mars, from its current state to a planet where humans can stand unprotected in the open air and breathe freely, is estimated by most serious researchers to require somewhere between 1,000 and 100,000 years, depending on the specific scenario and the level of active intervention applied. This is a timescale that challenges conventional human thinking about planning and purpose. Civilizations that commit to terraforming Mars are committing to a project that will not be completed by anyone alive today, or by their children, or by their children's children for many generations. But civilizations do undertake multi-generational projects. Cathedrals were built over centuries. Forests were planted that the planters would never see mature. The timescale of terraforming is different in degree, but not necessarily in kind from other long-term investments in the future. The physics says it is possible. The engineering is within the range of what a civilization with substantially more capability than we currently possess could accomplish. The question of whether it is worth doing is not a physics question. It is the oldest kind of question. What do we want the future to contain, and are we willing to pay for it?